The world around us is made of fluids in motion. The air we breathe, the water in rivers and oceans, the clouds in the sky, the blood in our bodies. Describing this motion mathematically is one of the oldest and deepest tasks in science. The equations that do this are called the Navier-Stokes equations. They are compact, elegant, and at the same time, they represent one of the greatest challenges in modern mathematics. Today, I want to present a new way of looking at these equations, not as a complete solution, but as a mathematical program that clarifies a crucial structural mechanism in fluid behavior. This program is called Dynamic Transversal Decoherence, or simply DTD. The Navier-Stokes equations describe a delicate balance between three fundamental effects. First, nonlinear transport. The fluid carries itself along, forming vortices and complex structures. Second, pressure, which acts instantaneously to redistribute motion and prevent extreme imbalances. And third, viscosity, which dissipates energy, the internal friction of the fluid that tends to smooth motion over time. The great challenge is not writing down these equations. The challenge is understanding how complex structures can arise and persist across multiple scales, from tiny turbulent eddies to large-scale currents. To study this, mathematicians and physicists use a central concept, vorticity. Vorticity measures how much the fluid spins locally. Imagine placing a small paddle wheel inside the fluid. The speed at which it spins gives you the magnitude of the vorticity. But there is something even more important than how fast the fluid spins: the direction of that spin. In other words, around which axis the fluid is rotating at each point in space. For decades, there has been a fundamental suspicion in fluid theory. If vorticity vectors in different regions and at different scales remain persistently aligned, this could sustain extreme behaviors of the flow. In other words, the key question is, can the flow itself continuously rebuild this directional alignment, even while viscosity is constantly trying to destroy it? For a long time, it was not possible to completely rule out this scenario. This was one of the last unresolved structural mechanisms. This is exactly where the Dynamic Transversal Decoherence program comes in. The central idea of DTD is simple to state, but profound in its consequences. Instead of looking only at the magnitude of vorticity, the program studies the dynamics of the vorticity direction field. Each vorticity direction can be viewed as a point on the surface of a sphere, a geometric sphere known as S. This change in perspective is powerful because the sphere has positive curvature. Moving on a curved surface is fundamentally different from moving on a flat plane. DTD shows that three effects act together on this geometric stage: the curvature of the sphere, which introduces geometric rigidity; viscous diffusion, which spreads out the directions; and transport-induced mixing, which continuously shuffles these directions. The combination of these three effects creates a robust mechanism that destabilizes sustained directional alignment. Transversal coherence refers to directional alignment between structures at comparable spatial scales, for example, vortices of similar size. The Dynamic Transversal Decoherence program asserts that this coherence must dynamically decay over time. The only way to preserve it is for the flow to develop extreme spatial concentration of energy. In other words, either the alignment breaks down or the fluid must concentrate into increasingly smaller regions of space. Demonstrating this rigorously was the main technical challenge. The work provides a complete mathematical verification of this mechanism, showing that the decoherence persists after scale decomposition. It remains stable under irregular transport, and it can be analyzed using modern micrological tools. The main result establishes a uniform in-scale decay of transversal angular coherence under standard analytical assumptions. The entire development is theoretical, autonomous, and self-contained. It is important to be absolutely clear: this work does not solve the global Navier-Stokes problem. It does not claim global regularity. It makes no extraordinary promises. What it does is something equally valuable in mathematics: it eliminates a specific structural scenario that was previously not technically closed. In science, understanding what cannot happen is just as important as understanding what can. The Dynamic Transversal Decoherence program introduces a new geometric and micrological layer to the understanding of vorticity dynamics in three-dimensional fluids. It places precise mathematical constraints on how vorticity directions can organize over time. This work was developed by Alex D. Oliveira Cruz, an independent researcher, and is part of a broader program on geometric rigidity in fluid dynamics. If you would like to explore the articles, preprints, and full materials of the DTD program, click the link below this video, where all files are publicly available. Thank you for watching. If this content helped you see the Navier-Stokes equations from a new perspective, please like the video, share it, and feel free to explore further. See you next time.